Welcome to the next part of the chapter Solutions. Till now we have seen that whenever a solute is added in a fixed amount of solvent, it makes a solution. But whatever we have studied till now, in that both solute and solvent were volatile. Will there any impact on the properties of the solution if we change the nature of the solute to non-volatile? Non-volatile solutes are like urea, glucose, cane sugar, etc. So if a non-volatile solute is added to a solution, definitely it will change its properties. Now, in today's video, we are going to see what are the changes in the properties, how these changes occur, etc. So let us begin. Suppose I have taken one closed container which is filled with a pure solvent, let's say water. In this, all the molecules which are present at the surface are available for the evaporation, and therefore vapor pressure caused will be totally due to molecules of pure solvent. Now suppose I have taken another container in which now I have added non-volatile solute such as urea or glucose. So now it has become a solution. Now what are the changes? In this now some of the surface area molecules will be occupied by the non-solute particles. Now since some of the places will be occupied by these non-volatile solute particles, the number of molecules of solvent which will be evaporating and creating vapor pressure will be less. As a result, I can say that vapor pressure of solution and vapor pressure of solvent, if we compare them, the vapor pressure of solution will be always less than that of vapor pressure of the solvent. We know the boiling point and vapor pressure, they are inversely proportional to each other, and therefore we will say the boiling point of the solution will be always greater than the boiling point of the pure solvent. This is one of the important topic. Many types of questions are framed on this, that why vapor pressure of solvent is greater than that of vapor pressure of solution, or why boiling point of the solution is greater than that of boiling point of pure solvent. Based on this, we'll discuss our next things. Now since we have seen the vapor pressure of the solution and vapor pressure of solvent, there are changes. Can we calculate the change in the vapor pressure? Yes, obviously. Let us see how. We know that total pressure equals to PA plus PB, where A stands for the solvent and B stands for the solute. Now this being a non-volatile solute, it will not give its any contribution towards vapor pressure, and therefore we are going to ignore this term. So I can write as total vapor pressure equals to PA, but we also know PA equals to PA naught XA. We also know XA can be also written as 1 minus XB. Rearranging and solving this equation, we get XB equals to PA naught minus PT upon PA naught. Or I will say the mole fraction of the solute can be calculated by pressure of the pure solvent minus pressure of the solution upon pressure of the pure solvent. Now in this, the term PA naught minus PT stands for lowering of vapor pressure, whereas the term PA naught minus PT upon PA naught stands for relative lowering of vapor pressure. This relative lowering of vapor pressure, this is your first colligative property. This is most important topic sure questions will be there from this topic, either the numericals or give reasons or MCQs or application based question, one liners, anything can be asked. But remember, this is a very important topic. So let us first discuss what are colligative properties. So what are colligative properties? Colligative properties are those properties which depend on the number of solute particles in a definite amount of solute, but not on the nature of the solute. Or I can say it is independent of physical or chemical properties of the solute. Whatever the melting point of solute may be, boiling point, density, or whatever the chemical ways it reacts, that is not going to matter. Then what is going to matter? The number of the solute particles, or I will say the amount of the solute particles, or the number of ions of the solute particles, or number of moles of solute particles present in the solvent. Sorry, this is solvent. That is what we call as colligative properties. There are four types of colligative properties: relative lowering of vapor pressure, elevation in boiling point, depression in freezing point, and osmotic pressure, about which we have already started with relative lowering of vapor pressure. Let us see in detail for that. So relative lowering of vapor pressure, just now we have seen xb equals to Pa naught minus Pt upon Pa naught. But we also know xb equals to Nb upon Na plus Nb. Now Raoult's law is applicable for ideal solutions which are very dilute in nature, and therefore we are going to ignore this term Nb. So now xb becomes Nb upon Na, or xb becomes Wb upon Mb upon Wa upon Ma. This is equation number 2. Comparing equation 1 and 2, we get Pa naught minus Pt upon Pa naught equals to Wb upon Mb upon Wa upon Ma. Rearranging this equation, we get Mb equals to Wb into Ma upon Wa into Pa naught minus Pt upon Pa naught. So this is your formula which will be important with respect to numericals. Mole fraction of the solute, molar mass of the solute indicated by Mb, that is equal to Wb, that is the mass of the solute, Ma, molar mass of the solvent, Wa, mass of the solvent, into Pa naught, that is pressure of the pure solvent, minus Pt, total pressure, upon Pa naught, that is the pressure of the pure solvent. So this is how relative lowering of vapor pressure means. Continuously we are saying that vapor pressure is inversely proportional to boiling point. So obviously it will affect on the boiling point. It will increase the boiling point of the solution. So now we are going to study our second colligative property, elevation in boiling point. So let us study elevation in boiling point, but before that let us recall the definition of boiling point which you have studied in your junior classes. It is the temperature at which vapor pressure is equal to atmospheric pressure. Now let us try to understand this phenomena with the help of a graph of vapor pressure against temperature. Suppose I want to plot the graph for a pure solvent. As the temperature increases, more and more molecules of solvent will evaporate, and therefore its vapor pressure will go on increasing. So this curve represents for that of solvent. Now suppose this is 1 atmospheric pressure where the vapor pressure becomes equal to atmospheric pressure, and therefore this temperature will be the boiling point of the pure solvent called as Tb naught. Whenever we are writing the symbol of naught, it stands for the pure or the standard one. Now when I add non-volatile solute to this solvent, just now we have seen that the vapor pressure decreases, and therefore the curve goes like this. for a solution. Again, this is 1 atmospheric pressure where it becomes equal to vapor pressure, and therefore it will be the boiling point of the solution denoted as TB. The difference between these two is called as del TB or elevation in boiling point. So del TB can be calculated as TB minus TB naught, where TB represents the boiling point of the solution and TB naught represents the boiling point of the pure solvent. Mathematically or experimentally, it is proved that del TB is directly proportional to molality. Introducing the proportionality constant, del TB equals to Kb into m. Now, since we are discussing about boiling point, we have taken it as Kb. Now, this is again the formula for which you will have a lot of numericals. Del TB is elevation in boiling point. Kb is known as molar elevation constant or abelioscopic constant, Kb. It is different for different solvents. As the solvent changes, the value of Kb will also change. The SI unit of Kb is Kelvin kilogram mole inverse. How can we define Kb? Kb or molar elevation constant can be defined as the elevation in boiling point of 1 molar solution, or I can say elevation in boiling point when 1 mole of a non-volatile solute is dissolved in 1 kilogram of solvent. Just now we have seen that del TB equals to Kb into m. But since this is molality and therefore del TB equals to Kb into Wb into 1000 upon Wa into Mb. Again, you have to use this formula which is important for the numericals. What are the terms in this? Del TB stands for elevation in boiling point. Kb is the abelioscopic constant. Wb will be the mass of the solute. Wa mass of the solvent, and Mb is the molar mass of the solute. So again we can rearrange this as the Mb equals to Kb into Wb into 1000 upon Wa in del TB. All these formulas are important for your numericals, as whole colligative property topic is important with respect to numericals. The numericals can be asked in 1 mark question or a 3 mark question, but colligative property and its related numericals is a sure question. So dear students, let us move on to solve some of these numericals. So here comes the first numerical. The vapor pressure of pure benzene at a certain temperature is 0.850 bar. A non-volatile, non-electrolyte solute weighing 0.50 gram is added to 39 gram of benzene. Vapor pressure of solution now becomes 0.845 bar. What is the molar mass of the solute? So first of all, let us write down the data given in the numerical. We want to calculate the molar mass of the solute. Vapor pressure of pure benzene is given. Pure benzene, that means Pa naught is given 0.850 bar. Immediately write down that of solution. Vapor pressure of solution is given. Pt is given 0.845 bar. Non-volatile, non-electrolyte solute weighing 0.50 gram. That means Wb, the mass of the solute, is given 0.50 gram to 39 gram of benzene. That means Wa, mass of the solvent, is given 39 gram. And we know that molar mass of benzene is 60 gram per mole. So we will use the formula related to that of relative lowering of vapor pressure. So this is the formula just now we have seen. Now let us substitute the value. The value of WB is 0.50. Molar mass of benzene is 60 upon mass of the solvent is given 39 into PA naught, that is pure one, is given 0.850 minus total is given 0.845 upon PA naught is again 0.850. So solving this totally, we get the answer as 170 gram mole inverse. So next numerical, molar elevation constant for benzene is 2.52 Kelvin kilogram mole inverse. A solution of some organic substance in benzene boils at 0.126 degrees Celsius higher than benzene. What is the molality of the solution? So we have to calculate molality. Molar elevation constant, that means Kb for benzene is already given to you, 2.52 Kelvin kilogram mole inverse. And this elevation in boiling point is directly given to you. Del Tb equals to 0.126 degrees Celsius. So a very simple numerical straight formula, del Tb equals to Kb into m. Del Tb is given 0.126, Kb is given 2.52, and we have to calculate molality. So substituting values and solving, we get the answer molality equals to 0.05. So this is the numerical now. The next one, which is based on elevation in boiling point. What would be molar mass of compound if 6.21 gram of it dissolved in 24 gram of chloroform to form a solution that has boiling point 68.04 degrees Celsius. The boiling point of pure chloroform is 61.7 degree. Given that Kb for chloroform is 3.63. So let us first write down whatever information is given. We have to calculate the molar mass of the solute. 6.21 gram of solute is given. So WB equals to 6.21 gram. Dissolved in 24 gram of chloroform, that means the weight of the solvent is 24 gram. To form a solution that has boiling point 68.04 degree, that means Tb is given 68.04 degrees Celsius. Tb naught is given 61.7 degrees Celsius. Okay, so first of all we'll find out del Tb. Del Tb equals to Tb minus Tb naught, that is 68.04 minus 61.7, and this becomes equals to 6.34 degrees Celsius. So we know this formula already. Mb equals to Kb into Wb into 1000 upon del Tb into Wa. Let us substitute the values. The value of Kb is already given 3.63 into Wb value is given 6.21 into 1000 upon del B we have already calculated 6.34 and Wa is given 24. By solving this we get the answer as 148.15 gram per mole. In all these numericals, I have taken one care that every time I have written the information given in the numerical, I have written the formula every time, and final answer is accompanied by SI unit. This you have to take care in your board exams also. Again, I am repeating, dear students, colligative property is an important topic. Numericals are sure one. So why now you people try to solve some questions on your own? So this is the assignment for you people. Go through the video carefully and you can write your answers in the comment section. Thanks for watching. Have a nice day.